that can actually be lifted. So I'll mention along the way when actually we can, when there are directions in which things I say will be generalized or can be generalized. And so it might, at first glance, not seem related to everything you've heard so far, but hopefully by the end of the exercise sessions, you'll have an idea that actually it's connected to probably everything you've heard. So yeah, that can be integrable systems like we've heard before, moduli spaces of curves, intersection theory, topological recursion, of course, and resurgence even. Okay, so this is a story in quantum field theory. And quantum field theory has a complicated history, right? So somehow I would say that mainly the quickest way to describe it is that the English language is not associative, right? So are we talking about a quantum version of field theory, or are we talking about a theory of quantum fields? And so therefore we have to understand what we mean by that. Okay, so quantum version of field theory is the kind of more traditional approach, which somehow has to do with, say, the Feynman asymptotics of some objects that you would like to define, and that eventually you want to use resurgence techniques to define properly. So heuristically speaking, this had to do with path integrals and this kind of nonsense, if you wish, but this could be given a proper definition somehow, at least a proper program to follow, and that if that program works, should give a well-defined object. Okay, so mathematically speaking, this is related to somehow deformation quantization. So I'm just going to drop a few words here and there for the introduction, right? So don't worry if you don't know the various things I'm mentioning here. It's all right. I won't mention them anymore again. So, okay. So deformation quantization, maybe WKB analysis, and so on. Okay. And well, all right. So that's one point of view. And on the other point of view of what QFT might mean in this non-associative picture of English, you might want to define what the quantum fields are themselves, right? So somehow the idea is that if you had a classical field somewhere defined on space-time, then it could have fluctuations here, fluctuations there, but at the quantum level, there is no reason why such an object should be defined all over the place, right? So the question would be what are quantum fields per se? And so there are different ways to think about this. One way is through the notion of vertex operator algebras, so VOAs. So I won't talk about VOAs, but they will be in the background all around, all during the lectures. And I believe the coming lectures will do the same dance as well, meaning that I'm not sure you'll see a definition of those, but they are in the background of many things you will hear from now on. So, okay, VOAs. And then another way to tackle the issue is to actually not think about the fields themselves, but actually the numbers or the functions you want to construct from these fields. Okay, and so these are amplitudes or correlation functions, and somehow ways to bypass the issue of or the algebraic issues of say, vertex operator algebras is to actually consider symmetries, okay, or an underlying geometry that would allow you to characterize the correlation functions or amplitudes you're interested in. And so this brings us to the main topic of this course, which is quantum geometry, or at least I'll try to motivate is a geometric framework that you can call, or that you can label by the word quantum. Okay, so in particular, using geometric considerations, we will try to define, or actually, okay, so yeah, define non-perturbatively, okay, some holomorphic amplitudes or partition functions, depending on the point of view you want to adopt, that ultimately would be, say, candidates for the resurgent resummation of topological recursion partition functions, so which I think you've heard about in the last days. Okay, so, but all right, so but what is yes?
Ultimately, it's two points of view should produce the same result.
You wish? Yeah. But yes, I mean, that's basically the philosophy. But then before being able to compare objects, you should define them, right? Be able to calculate them and find ways to bridge between different approaches. And all these steps, I think, are non-trivial. Right? So, okay, so quantum geometry could be the topic of books with maybe thousands of pages, right? It can go from non-commutative geometry to maybe ideas like quantum cohomology or things like this, and somehow I don't think it would be even possible for me to, with my knowledge, to give justice to the topic itself. But for us, it will be a geometric framework that parallels the theory of Riemann surfaces, or actually the theory of spectral curves. Okay, so as you now know, spectral curves are Riemann surfaces plus, or actually coverings of Riemann surfaces plus some data, right? So this, we'll come back to that later. And okay. All right. But somehow the idea is that contrary to the right-hand side of this equality, we will not try to quantize in any perturbative or deformative way a classical theory, right? We will directly work with h bar equals 1. Okay, and so this is somehow non-perturbative, right? So to relate to, say, resurgence considerations, the story I will tell is what you should obtain after performing all the steps of a Borel resummation and set your singular perturbation parameter to 1. Okay, are there any questions so far? All right, good. So, okay. right, so let's see, let's try to motivate that geometric framework. Okay, so to do so, let's consider a certain dynamical system, or a certain type of dynamical systems, which are called lax pair dynamics. Let's call it this way. Okay, so this takes the form dl by dt dl by dt equals the commutator with R and L, where L actually depends on two variables. One I call x and the other one I call t. Okay, and this is for us a matrix valued one form of the variable x, say on the Riemann sphere. Okay, so here already you see somehow two concepts that appear. One is that of matrices, and the other one is that of the Riemann sphere. And everything I will talk about in these lectures can be generalized to any reductive complex Lie algebra on, and here, on any compact Riemann surface. But to avoid any unnecessary complications, we'll just stick to matrices on the sphere. Okay, and R depends on the same variables, but is just a matrix valued function. Valued function of so x in P1 and say T in C. Okay, so first exercise. So yeah, so this is how I think things are going to happen. There are going to be a few exercises that I just cite along the way, and we'll so you can try to do them whenever, but if you can also ask me about hints or whatever. And so tomorrow during the exercise session, there will also be other exercises to relate what we are talking about to other lectures you might have attended during this conference. Okay, so exercise 1, show that the surface defined by the characteristic polynomial of the matrix L, so something like this, y minus, so yeah, basically the pairs xy such that the determinant of y minus L of x and t is equal to 0 does not depend on time. Okay, so here you might ask, what is this y variable? Okay, so since L is taken to be a one form of x, okay, here y is interpreted as a coordinate in the fiber of the cotangent space to P1. Okay, and so this curve here is actually sits in the cotangent space to the Riemann sphere. Okay, so all right, so this object here is something you can call the spectral cover. Okay, so now you might notice that here I write cover, there I write curve. Okay, it's because here the spectral curve is defined as this covering of Riemann surfaces plus some additional data. which here is not included in the definition of the spectral curve. Yes. Yes. I mean, if it was sigma minus something, it would be smaller, right? Okay, but yes, thank you. All right, so what we get is a covering of a base. Okay, so let me call this P1 here curly C, like this, just to kind of emphasize that you could think that it's actually another Riemann surface and it wouldn't really change the story. So yes. This is the meromorphic one form. Okay, and here this is meromorphic as well. Yeah, thank you. Okay. All right, so I'm going to try to draw something like, say, you have maybe sigma that looks like this. You have the base C. This projects. This is the map X, right, that projects onto the first variable. And this sits into the cotangent space, and you can project back down with the with the natural projection of that bundle. Okay, so here you have something which is like that. So over a point X, you have various pre-images here, there, and there. Okay, and the idea is that a point upstairs, right, can be described as a point downstairs plus the data of a sheet index. Okay, and this is well defined, at least locally, until you reach some special points, like here, where two of the sheet indices become indistinguishable. All right, and the so somehow that means that over a point X, right, you'll have three. In this case, you'll have three pre-images, right? And so when you project down, it looks like they are vertical, if you want. But instead of seeing them vertically, it might be interesting to just rotate this by 45 degrees. And instead of seeing the three pre-images, say Y1, Y2, and Y3, right? So Y1, Y2, Y3, that you could put into a vector. You could think of those actually as the coefficients of a diagonal matrix. Okay, so that might sound a little silly at first, but the idea of the quantum geometry I'm going to describe is to consider that a quantum spectral curve, instead of being described by a point on the base plus sheet indices, right, it will be described as a point on the base plus, how do you say, to transpose, to exchange two sheets, right? And, well, in this new picture, what you can do, additionally to just permute sheets, is to actually superpose them, okay? And so if you think about superposition, then this is like acting with the linear transformation on this vector here, or this diagonal matrix here. And so now instead of having sheets, you end up having a vector bundle over the base. And when you move around the base, what you can do is act linearly on these vectors, okay? And so this hints at the fact that the quantum version of a spectral curve should actually be a vector bundle with a connection. Yeah.
In this picture, what role is played by the dimension of the matrices?
Well, so far none. Yeah, could be any. Right? Basically, the size of that matrix, right, is the degree of that polynomial. So it's the number of sheets, right, in the covering. Okay, and therefore it's the, if you want, the dimension of a Cartan subalgebra of your Lie algebra, right? Which for us will just be, so since we have matrices, it will just be the size of the matrices. Any other question? Okay, so all right, so complex reductive. But for us, just GLN today, yeah. Okay, so definition. Okay, so instead of going through bundles and connections and whatnot, I'm just going to define a quantum spectral curve. Okay. All right. To be a matrix valued meromorphic, or actually rational, differential system of the form. Okay, and so here basically we're going to see all the words that appear in the title. Okay, so of the form dm equals commutator of phi and m, right? So here you see that the letters change from here, okay? And so this was supposed to be classical, all right? And you had a time dependence, okay? And it's something which is independent of time that here we are quantizing, okay? So this dynamical system here is not at all the one there, okay? This is first remark. And second remark is that this L here, which was a matrix valued meromorphic one form, is actually connected to phi here, okay? But here, remember that this is to be thought of as living when h bar is equal to 1, okay? And this is when h bar is equal to 0. And L here on the left board is actually the limit of phi when h bar goes to 0. But there's no h bar here, okay? But that's the idea. Okay, so a rational differential system of the form dm equals phi m with so phi of the form sum from j equals 1 to m of phi j over x minus pj, okay? So if this is our Riemann sphere, you can mark a certain number of points on it, okay, where the differential system actually has simple poles in this form, okay. The hypothesis of this form of phi is the Fuchsian hypothesis, okay. And so you might have seen somewhere else another definition of what a Fuchsian differential system is, and it connects to that definition here by the fact that for any matrix E, okay, you can define a solution of that linear equation here by conjugating the matrix E, okay, by psi of x, where psi of x is invertible and satisfies d psi equals phi times psi. Indeed, because phi is a connection potential, so it's a one form. Thank you. Okay, so if you start from this equation here, okay, that you can write nabla psi equals 0 with nabla being d minus phi. So, by the way, here I wrote x, and I said x lives on the Riemann sphere. So this, say, if P1 to Pm are in generic positions, then this is basically in the infinity excluding chart. Right? Just remove a point and write it this way on the complement. Say again? Well, psi is the solution of d psi equals phi psi. All right, and so if psi is an invertible matrix, okay, then you can think of it as the fundamental matrix solution of a vector differential equation. All right, and this vector differential equation, the fact that phi only has simple poles, tells you that if phi could take the form of a companion matrix, then the ordinary differential equation you would obtain is Fuchsian in the usual sense. Okay. Yeah, simple. No, it's just the fact that phi has only simple poles. You mean? Yeah. No. Yeah, no. This is what I said. Like somehow you have x in P1, and you, if you choose a point, you call it infinity. You remove it, and in this chart you want phi to take this form.
Local around x equals P1.
Yeah. No, not x equals P1. Sorry.
You said that x is a coordinate, a local coordinate.
And
this equation, I mean, this is supposed to have, is it a formula for?
Yeah, it's a formula for phi.
All over.
Well, I mean, no, because you don't have a global coordinate.
It doesn't mean that it's like
This here? No, what I'm saying is that if you take this m here, that you define in such a way, so if you want, I can put rather a comma here. Okay, so m depends on e and on x in such a way where psi solves this equation. And now, if you want, exercise 2, show that this equation here solves the quantum spectral curve. E? Sorry.
What is matrix
E is just a matrix. Right?
General solution of your system T2M.
Yeah, exactly.
E is kind of initial point.
Yeah, exactly. You can think of it this way, right? So here, if you take a reference point like that. Okay, so just for concreteness, let me here say that we take matrices of size n, right? N by n matrices, and over a reference point O, you can have this matrix E, okay, that belongs to Mn of C. All right, and in such a way you can think of E as an initial condition. But just formally, if you have a solution to this equation, then for every fixed E, this solves that. Yeah, exactly.
I think like we have this Lex equation, but we can rewrite it in small, right? It's the same.
No, not really, not really. So this is what I was explaining before, right? This phi plays the role, I mean, basically this connection here, nabla d minus phi, plays the role of the quantized L. Yeah. Mm-hmm.
And then you put a phi solution to that. Now you define m this way, and you update it and this phi is the first equation. The first equation is actually the answer.
So, almost. Start from phi, right?
So you do it at the final side.
Exactly, yeah.
So you define m this way, and now you check that m is the type of equation.
Yeah, you check, it's an exercise. So, yeah, yes? Sorry, say again?
There's some sort of n that satisfies this.
Well, okay. Come back to classical dynamics, right? So you have this lax dynamics here, okay? And L is basically your variable, right? It's the values of L describe your system, okay? The quantum version of L is phi, right? So this is what phi is. So phi becomes basically I mean, yeah, basically that's the point, right? Is that the idea is to transform what would be the quantization of L in the usual sense, right, to some geometric objects that allow to encode the properties that your observables should satisfy. Yeah, sure. Yeah. Yeah, exactly. Yeah. Yeah, if you have psi, then actually M is entirely solved. But somehow M is more important, even though the auxiliary psi will always be of use, or will be of use sometimes. Okay. Are there other questions? E is like the initial condition, right? It's not exactly this way, but if you think of psi as parallel transport by the connection, then you see that E will be the initial condition of M at some reference point O, and you can parallel transport it to any point. Yeah. Yeah, yeah, exactly. Exactly.
Wait, sorry. So E is also part of the initial data of the funds.
No, E is a parameter. Because for any E, this solves that. Yes. Okay. So maybe this helps. All right. Okay.
And we have, I think, the break between the last line.
So here, what I'm saying is that if instead of starting from this equation here with the commutator, you start with this one, with just a product here, then if you have psi, then you have m through this for all e. Yeah, exactly. Nothing more.
So if we different initial conditions, what would be possible like the same exactly?
Sorry, what do you mean? If I take different initial conditions? Yeah. Well, that's the thing, right? Is if you take f here instead of e and you do the same conjugation, then you just get another solution. So you have as many solutions, right? So this is a linear equation on these matrices, and it has as many solutions as these initial conditions. Yes? Matrix, yeah.
Depending on the E
Well, so this yeah, so this will be in the exercise session. Basically, if you have a basis for matrices, what happens to M? What does M look like? Yeah. Well, for dimensional reasons, yes. Right? Exactly, because if you vary E, you saturate the dimension of the solution space. Okay. Any other question? All right. Okay, so since phi has poles, simple poles here, if you take this invertible function psi and you take it around, so you say you start from a point x and you analytically continue it around a certain non-contractible cycle, okay, then what you will actually obtain is another solution of your differential equation. And that means that you can write the action of the fundamental group of the punctured sphere on the space of solutions to this differential equation. So I1 of say, so here we had C, say CP, okay, where CP is curly C minus, so maybe now you want me to do something like this, like that, and you write it in such a way, psi of x times a certain matrix S gamma, where S gamma is invertible. Invertible. Okay, so now exercise 3. Okay, show that this invertible matrix is actually constant. Okay. All right, it's not very hard actually. All right, and so in such a way, if we have an S gamma which is constant for every element of pi 1 of CP, this defines for you what is called the monodromy representation. Okay, S, which is a representation of the fundamental group into invertible matrices size n. Defined in such a way. Okay. All right. So quantum spectral curve is basically this connection, okay, but acting on matrix valued objects. All right. As a connection, you can define in such a way its monodromy representation, okay, and also you can use nabla. So nabla d minus phi can be used to parallel transport along arcs. Okay, so in the in the previous courses, you have probably learned that a spectral curve should be this Riemann surface, but additionally it should have some geometric objects, right? And so one of them was this omega 01, and the other one was omega 02. Okay, and if you wish, in omega 01 and omega 02, the zeros stand for classical. Okay, and so we will define a W1 and a W2 from the data of the quantum spectral curve, which play the role of omega 01 and omega 02. All right, but this you'll have to wait for that. Okay, but all right, so back to the heuristics here. Okay, so the point of the spectral curve is a point on the base plus a sheet index. Okay, and you can do the same for the homology. So say you take a path downstairs, right? So maybe I shouldn't actually draw it here. So that, okay, so that was x. Okay, so if you take a path upstairs, say this so yeah, basically locally, as long as you don't go through ramification points, which are these points where sheets meet, okay, if you take a path, say, upstairs, you can realize it as a path downstairs plus the information of if you cross a ramification point or not. Okay, so let me explain. If a point upstairs, say you have a path, okay, so it looks contractible here, but maybe the covering has a higher genus and it goes around non-contractible cycle, so it's not necessarily contractible. But if you have a path upstairs, it can project down, okay, and if you're away from ramification points, then the fiber is just, if you take basically an open set around here, right? If it doesn't meet branch points, then its pre-images by the projections would just be copies of that open sets, of these open sets, right? And okay, which means that if you take non-contractible cycles upstairs, right, either they go through ramification points or not, but if they don't, then they are basically described by non-contractible cycles downstairs plus sheet indices. Okay. Now, so this is for closed loops. But now you can have a open arc upstairs, okay, which projects down to a closed loop downstairs. All right, and so you see that here, to describe such open arcs, you need both the closed loop downstairs and the information that you're changing sheets upstairs. Okay, so now, that being said, so now definition again. Okay, the quantum homology, right, or the homology of the quantum spectral curve, okay, will be defined as the homology on CP, okay, so meaning the homology on C relative to P1 to Pn, okay, but with local coefficients defined by the connection nabla through parallel transport. Okay, remember that parallel transport is the quantum analog of basically moving upstairs on the covering. So if you move upstairs, what you can do is either come back to where you started from, okay? That's a way to have a closed loop downstairs. But another way to have a closed loop downstairs is to have a path, okay? And a starting point, right? And basically the deck transformations of that covering will tell you how to transform the starting point into the end point. Okay? And this is what is generalized in the parallel transport. Okay? So the monodromy of the connection generalizes the deck transformation group of the covering. Okay? It is. So, okay, so here short answer is that if you do, so the answer to your question, yeah, it is quite different. This is quantum homology, not the same. Yeah. Yeah, this is the monodromy representation, right? Here, what I call quantum homology is the homology with local coefficients. is the homology with local coefficients, right? And why do I call it quantum? Is that if you consider this construction, but not for connection, but for H-bar connections, and you perform WKB analysis, okay, then the classical data you obtain by the WKB analysis will be that of a spectral curve, okay? And so through this WKB quantization, if you want, what you obtain by, yeah. Well, no, because okay, because Pauli 6 is an isomonodromy problem. Now you're saying if you quantize the isomonodromy problem, but I'm not quantizing the monodromy problem, I'm quantizing the spectral curve. Okay, so this is not to be confused. Like if you, what I'm trying to motivate is that if you start from I don't know. Yeah. No, I know the definition of the quantum spectral curve that you obtain by this determinant. Well, why? Why should it be the same? If you, sorry, can you repeat that sentence? Okay, yes, please. Okay, no problem. So, okay. Anyways, the quantum homology is the homology on C relative to the poles of the connection with local coefficients defined by the connection through parallel transport, okay? So this, let me denote it just H1 hat, which is basically the homology on the pointed Riemann sphere with local coefficients defined by the connection. So what does that mean? That means, so I'm going to explicit what this is. Okay, so in the holomorphic case, this was defined by Goldman. Okay, so holomorphic case on Riemann surfaces, this is due to Goldman. But in general, if you have a connection in a principal bundle over a Riemann surface, which is actually holomorphic, and you consider the homology with local coefficients relative to that holomorphic connection. Okay, but here we're looking at the sphere with a meromorphic connection, so it's a slightly different case. But in any case, this H1 is constructed from, so basically it's generated by chains on the base, okay, weighted by matrices, right? Because each of these matrices is enough to be parallel transported by the connection, and you define the boundary of such a tensor product to be the initial point weighted by your matrix. So actually, no, let's the final point weighted by the parallel transport by the connection along gamma of that matrix E minus the initial point weighted by the matrix itself. Okay, so that's the formula, but you drop So dropping endpoints that belong to P1 to Pn. Okay, it's relative to the poles of the connection. All right, and then this H1 is basically the kernel of the boundary operator. Okay. So for any gamma in any matrix E, you can define the boundary in such a way. Then you can take linear combinations of these, and you're interested in the vanishing boundary condition. Okay. So these cycles can also be intersected, and so the way to intersect them is that if you have gamma 1 E1, you can intersect it with gamma 2 E2. Okay, so maybe I'll just put a hat here as well. And now this becomes the sum over the intersection points of gamma 1 and gamma 2. Okay, with the orientation factor corresponding to that intersection of the trace of the product, okay, of what I call sigma 1 of Q times sigma 2 of Q, where sigma I, so maybe in green, where sigma I of Q denotes the parallel transport of EI from gamma I of 0 to Q along gamma I. Okay, so you have this is gamma 1, this is gamma 2, here you have the intersection point Q. So you think, so it's like you have E1 here, you have E2 there, you parallel transport them with the connection until the intersection point, take the product, take the trace, orientation factor, and you sum over all the intersection points. I didn't change the thing. Yeah, so gamma is a cycle, it's a chain. Yeah, gamma is a cycle on the base. And sigma I is the parallel transport of the matrix E until the intersection point. Basically, sigma I is parallel transport along gamma I. Yeah, exactly. Okay, so yeah, it's a smooth chain. Second. Well, no, that's the thing, right? Is that I don't want to consider homotopy classes of the chains as is, right? I want to construct this h1 hat from these boundaries, from these chains here. So this is just a smooth chain, and E is a matrix. So this is not. So basically, here, these are not homotopy classes, but here you see that it only depends on that. Because the only way, if you want, since you have this trace here, if you move this Q a little bit, you will conjugate everything. And since the trace is conjugation invariant, you're going to get the same result. Yes. But so this, so you're actually sending me to where I'm going, which is what do these cycles look like, right? And can we actually count them and see the dimension of that space? Okay. Yeah. So you have these matrices that you take the product, you take the trace, and then you sum all of this with sign. Okay, are there other questions? Okay. So what do these cycles look like? Yes, due to the orientation factors. If you exchange gamma 1 and gamma 2, this is symmetric here, right? And this changes sign. Yeah. This is the definition of this hat intersection. Sorry, can you repeat? If they intersect on?
Ones that don't intersect at all, that's how they
So, well, the okay, so these here, you see that this, there is no sigma here. Right? So sigma was the classical picture. But here you can imagine some cycles that intersect downstairs, but have zero intersection here, right? Rather than the opposite, because of that trace of the product, right? Because you can have orthogonal or orthogonality for the trace, regardless of what happens for the cycles downstairs. Okay, so all right, so this is what we have. This this P1 here, and let me like redraw it in another way. Okay, so P1, P2, PM minus 1, and PM. Okay, and I'm just going to draw a graph on the surface in such a way. Okay, and using this graph, which has edges and vertices, right? So if this is gamma here, this graph, and this is C here, it satisfies the following properties. So the first one is that if you remove gamma from C, you get something which is simply connected. Okay, gamma has M external edges, M minus 3 internal edges, and M minus 2, I think, vertices. Okay, so all right, and so now we can use this graph here to engineer some generalized cycles, or these cycles with local coefficients. Yes? So a second. Finite dimensional? Yeah, okay. No, I think you're right. Okay, so basically this is the kernel of something which is a one chain, okay? And it should be modulo the kernel by, yeah, so basically the image by this guy, where now this one, say, let me put a 1 and a 2. Okay, now this one is defined on chains that start from the square, right, to C, and the boundary. So okay, thank you for noticing. So basically, the general definition of this guy will be the usual boundary on the base, tensor the restriction map on the boundaries. Okay, meaning that if you start, say, from so if you have, say, this is a one chain, now say this is a two chain, okay, and you can attach also to this point here a matrix, right, and you can still parallel transport it everywhere, okay, and then the boundary of this tensor that becomes its boundary, right, with the same matrix, right, because everything is contractible and everything is parallel transported anyways by the same connection. Okay. Yeah. Okay. All right. Any other question? Yeah, I hope they're all right. Okay. So what do cycles look like? So we have cycles of different kinds. So, okay, just to elaborate on this boundary operator, generalized boundary operator, you see that in such a way you can define it whenever you have a meromorphic connection over a manifold, basically, right? As long, and it doesn't matter if this manifold is a Riemann surface or higher dimensional, right? Because you can always restrict whatever sections you have to the boundary that you obtain by applying the boundary operator on the base. Okay, so the first kind of cycle we can consider is if we have an edge E of the graph and an edge of the graph and the corresponding non-contractible cycle that goes around that edge. So here it would be, for instance, for this one, it can be this one here, right, which is uniquely defined by the constraint that it crosses the edge, right, and not any of the other edges. Okay? All right. So now if we have this, what does it mean to have zero boundary? Okay, so this chain here, it has an initial point, which is the same as its endpoint. Okay, so the boundary, in fact, is gamma 0. Okay. And then we had the parallel transport along gamma of E minus E. Now, by definition of the monodromy representation that we introduced earlier, so if you remember, since you can construct any solution to the quantum spectral curve from E by conjugating by the psi function, right, that we mentioned earlier, that means that actually this parallel transport here is nothing else than, sorry, this was gamma E, is nothing else than the conjugation of E by the monodromy matrix. Okay? And therefore, gamma E tensor E belongs to the homology space if and only if, so gamma E tensor E, so this like that is equal to 0, if and only if E belongs to the kernel of a certain map that I'm going to write this way, where this is defined as the kernel, the map that conjugates by S gamma E and minus the identity. Okay, so generically, this has dimension n. Okay, so that's one example. Yeah. But I never know if that means that S gamma E is in the centralizer of E. Exactly. Right. Okay. So now second kind is if we have a vertex. Okay. And we can consider these contours. Okay, so basically this is, so around V, since every vertex is trivalent, you have 3 edges. Okay, each comes with a certain non-contractible cycle, and you can consider cycles of the form basically linear combinations. So this, so gamma E1, small e1 tensor big E1 tensor plus gamma E2 tensor E2 plus gamma E3 tensor E3 equals 0. Okay, so some of these cycles, not cycles of this form, will have vanishing boundaries. Right? And what we're trying to do is figure out which ones and what is the dimension of the linear space they span. So here, for instance, we had something I can call DE, right, which is the dimension of this centralizer of sorts. And so here, so of course there is no, it's not as simple as here. Right? Here we had only one path and one matrix, so we could just parallel transport it and compare the end value with the initial one and say that they have to be equal, and this gave us our constraint. But here it's slightly more complicated, right? You have these 3 terms that you add, okay? And So basically the dimension of the space you obtain, okay? So initially you have 3 matrices. So that's 3 times n squared dimensions, okay? But here we have an equality, okay, which takes place at this unique vertex, because there's only one single initial and end point for all these paths. All right? So that means that this equality here is one equation of matrices. Okay? So that removes n squared. Okay, so this is from this equality here. Right? Okay, then you also have the fact that these 3 paths, so gamma E1, gamma E2, and gamma E3, are actually not homotopically free. Actually, if you sum the 3 of them in this drawing here, you will actually get something that you can close behind. Okay, so the sum of these 3 paths is actually 0. Okay, which means that here you can write gamma E3 as minus gamma E2 minus gamma E1. And in fact, instead of having, like initially we could have thought 3 independent ones, we actually only have 2. So that removes another n squared. Okay, so this is because of this. Right? And additionally, we need to remove all the cycles of this form that we've already counted. Right? And so this becomes minus d E1, remember d is that, minus d E2, minus d E3. And so at the end, we get dV, which is n squared minus dE1 plus dE2 plus dE3. Okay? So back to the question, like, is this homology space even dimensional that was asked before? Basically, these cycles here, we denote them A, E, comma E. Okay, so this is suggestive. They will be paired with an equal number of other cycles in a bit, or actually tomorrow as exercise. So this will amount to an even dimension of cycles. And this thing here, right, generically, these Ds, I said, are n-dimensional. And so this generically is n squared minus 3n. And n squared minus 3n is even. Because either n or n minus 3 is even. Okay, so basically you see slowly how to construct these cycles, and the fact that they will, through this generalized intersection, be even dimensional and form in the end a symplectic space. No, that's not all. That was a question, right? No, that's not all. So, I'll have you calculate the exact dimension tomorrow. You, but there are not that many other types of cycles. So basically, if you have now, so you see we started from an edge, right? These edges, they can meet at a vertex. So now we are at a vertex, and we saw that if we remove this, we can still construct some cycles, okay? And now, if you take two of these vertices, you can put them together to form something like this, okay? And on this type of subpart of the graph, gamma, you can consider similar things, but instead now of closing on itself like we did for this vertex, you can go to the next vertex, like this. Okay, so let me call E the edge in the middle, E1, E2, E3, and E4 the edges that leave. Okay, and now here, one, two, three, four, 5, and 6 arcs. Okay, 4 of them are closed, and they close on the vertices, and 2 of them just go from one vertex to the next. Yes?
Let's say it's like connected E2 to E4 through an edge that's E1 to E3.
Sorry, I didn't get it. What do you mean?
Like E1, E2 meets in a vertex, edge, E3, E4 meet. So you said like you do 5 graphs, right? E2 and E4 meet in a vertex. There's an edge to E1, E3. It seems like there's not a unique way to construct it.
No. I mean, there is no unique graph like that. That's for sure. There are many choices.
Sure.
Yeah. And for all of these choices, like I fixed a graph, and for a fixed graph, you can construct all of these cycles. Okay, and so now the question is, can we find something which looks like 1 to 6, gamma I tensor EI equals 0. Okay, or yeah.
On the other side of the sphere and turn around.
And I come back, yeah, exactly. So for instance, here, I mean, just like for this one, I was going behind, but here, for instance, if this was this part here, then you have something like this, which is basically, which just goes around, right? So this is simply this one, and you have this one, this one, this one, this one. Okay, so how many cycles do we get? Okay, so you can do the same thing, right? So initially we have 6 free matrices, right? Then you have 2 homological relations similar to there. Okay, so that's only 4 left. Okay, then you have 2 vertices on which you have to make the boundary vanish. So that's only 2 left. Okay, so here we had something. Okay, so here the dimension. So we say we had 6n squared, okay, minus 2n squared for the number of relations, minus 2n squared for the homological relations, okay? And then we still have to remove all the cycles that we have already counted in the 2 ways before. Okay? So how many are those? Okay, so we have 2 vertices. So this is minus the first vertex. So this is n squared minus dE1 minus dE2 minus dE. And then minus, for the second vertex, n squared minus dE minus dE3 minus dE4. Okay. And then remove all the cycles associated to the edges. So that's minus dE1 minus dE2 minus dE minus dE3 minus dE4. Okay. So now let's count. Okay, so here 6n squared. So we remove 2, 4, 5, 6. Okay, so that goes. And then you see that there's a minus and a minus, so this becomes a plus, and then there's a minus here, so we remove them. So dE1 goes with dE1. dE2 goes with dE2. dE goes with dE. dE3 goes with dE3. And dE4 goes with dE4. So they almost all went, except one, this one here, okay, which tells us that actually these ones only have dE prime, which is the same as dE. Okay? All right. So, from what we defined as a quantum spectral curve, okay, which was this differential system valued in matrices with a flat connection, okay, we could define a homology with local coefficients, and this is what it looks like, right? These are combinations of cycles or chains actually downstairs together with matrices, and you can basically have these kind of weird chains, right, which are weighted and end up having vanishing boundaries. Okay, so how much is that so far? Right? So to each of those, we had dE, and now to each internal edge, right? Because every internal edge has this form. You can have the same number. And these ones, you see, basically, since these, actually these two directions here are supported by the same edge, right? You see that this one actually intersects this one for internal edges only once. Okay? And, all right. And then these had elements that are in the centralizer. And you see that here, the only degrees of freedom you have are actually the same, right? Except that the support is now on the edge, which is perpendicular to that closed loop earlier. And so these ones we call B, with the same edge and one element E to label it. Okay? All right, so here's a partial answer to the question that was raised. Is this even dimensional? Okay, so as far as internal edges and vertices are concerned, yes, right? And for the remaining ones, which are the external edges, which here comes with the same dimensionality, and we should construct additional ones. We'll see that tomorrow as exercise. Okay? And this will somehow directly generalize the method that we saw here. Okay, so exercise 4, I think. Okay, is basically calculate the dimension of that space, and actually I'm going to call it 2G. Okay, and what it amounts to is to guess what the counterpart to the external edge is to be associated yeah, basically that's all. Just to, so we'll see that tomorrow. Okay, so are there questions about this? Right? So yeah, this is definition of genus. You can see it this way, but I call it G. It's also suggestive that if you take the if you basically take an H-bar connection instead of taking this connection, this Durham connection that we have here, and you send H-bar to 0, right? What you will get is a spectral curve, and the genus is this number. Yeah. Okay. Are there other questions? So if we remove that graph gamma, the green graph, from the base surface, what we obtain is simply connected. So it basically looks like a fundamental domain. So let's define. Okay, so these are basically the cycles. But usually, what do you do with cycles, right? What are cycles? One way to see them is as a linear functionals on differential forms. Okay, so you can see cycles as something you integrate forms on to obtain a number. And here, what would be the counterpart to the usual differential forms that you would pair to such cycles? Right? So basically, if you take an element gamma, which is now a linear combination of matrix-weighted cycles or chains, okay, you can, that belongs to H1 hat, okay, then you can define the integral of an object omega on gamma as sum of the trace of omega of gamma I of t times sigma I t, right? Where sigma I has the same definition as earlier, which is the parallel transport of EI along gamma I. Okay, so that can be the definition. As soon as omega is a matrix valued one form on the base. Okay, so these cycles are just dual to matrix valued one forms on the base. Yeah, this is the way. I would see it. Basically, so this we will discuss that tomorrow. But if you deform the quantum spectral curve, okay, then you'll have a certain number of deformation directions that you can take, right? And these will, so if you want, by some homology calculations that we will do tomorrow, you can relate that to matrix valued one forms on the base. And by some other construction, you can also associate deformations to these generalized cycles. Okay? And so that we will see tomorrow how it exactly plays out. Okay, so here there can be issues. Here there can be issues because gamma might meet a pole of the form, right? And for that, you need to basically regularize in a way that I'm not going to write here, which basically consists in some kind of principal value type regularization. Okay, and so all right, so for the remaining 15 minutes, let's start by writing down a lemma that we're not going to prove here, but I'll leave it as so exercise 5. Say again?
I mean, you think you go
Because I thought we started at 15. Okay, all right. So, so then I won't prove the theorem that follows the lemma. I'll just write it down and finish here, and we can see the proof tomorrow. So basically, if omega is a matrix-valued meromorphic one form, then so matrix-valued meromorphic one form, okay, and U is a tubular neighborhood of the graph gamma that does not contain the poles of omega which are not in the poles P1, Pm of the connection. Okay, then there exists a primitive of omega on that tubular neighborhood. Then there exists F, which is a matrix valued meromorphic function. Function such that df is equal to omega. Okay, so there are primitives of these quantum differentials, right? Or these differentials that are valued in the matrices and that get paired to the cycles. And so to finish, and we'll start tomorrow by proving this. A theorem which I call the quantum Riemann bilinear identity. Okay, which tells us that if omega 1 and omega 2 are matrix valued meromorphic one forms, with df1 equals omega 1 and df2 equals omega 2 as per the lemma, so with a fixed tubular neighborhood U of gamma. Okay, and if AI for I equals for I from 1 to 2G is the basis of H1 hat. Okay, with intersection matrix Ij equals the intersection of AI and Aj. Okay, then the integral along the boundary of C sub gamma, so C sub gamma is simply C minus gamma, okay, of the trace of omega 1 times F2 is equal to minus the integral on the same boundary of the trace of F1 times omega 2. Okay, and this is equal to the sum for I and j from 1 to 2G of a bilinear expression of the periods of omega 1 and omega 2 along these basis elements. So that is AI omega 1, AJ omega 2, and in the middle here, you have the inverse of the intersection matrix. Okay. And since apparently I am already over time, I will stop here and we will start tomorrow by proving this. No, they are allowed. They are allowed. It's just that the tubular neighborhood has to be close enough to the graph that it doesn't contain the poles of omega that are not on the graph. So basically what you do is you remove gamma from the surface, okay, so you get this graph, and then you're basically along the boundary, and it's on this tubular neighborhood there that you can integrate. You're never crossing the graph. Yes. So if you want, U is a tubular neighborhood, so this was probably not well written. It's a tubular neighborhood of the boundary of the surface minus the graph. Are there other questions?
Thank